Okay, so this is the second part of the sort of documentation I'm making on this multi-party computation peer-to-peer network that I'm building for a Bitcoin bridge. So pretty much in the last document, I explained how I was working on the key generation process. So in this distributed system of whatever 12 nodes I have here now, 10 nodes, um, we can in secret construct a private public key pair between all the nodes where only each one of the nodes owns or knows a share of the key and not the full key itself. So using that, we can combine to sign transactions or sign data, which we can then use to validate or verify that something has or has not happened. So that's sort of the premises we will build off of in order to do a Bitcoin bridge from Ethereum to or from Bitcoin to Ethereum. So I've gotten the signing done now, and I've been recently just working on the Bitcoin API. So what that means is watching for a deposit, and when a deposit happens, um, sort of kickstarting this whole signing process. So it's not completely done, but it's another step in the documentation. So I will sort of explain how it will end up being with this example. So right now I have an API. I have implemented a blockchain which has very limited pBFT consensus for adding blocks. So there's a leader. So if we get the leader is the person who can start a new key generation, which means only the leader can create a new public key session between all of the peers in the network. So if I go to 3003 and start, then we will go through what you've seen on the last video, where we just generate the key between all these nodes. And at the end of it, we can derive a Bitcoin address that we want to lock assets in order for us to mint. So when all of the sort of key generation proofs get finished being verified by all of the peers in the network, we can get the final public key and derive from it using the appropriate methods the Bitcoin version of what that public key address would be. So when all of the nodes verify that a key has been successfully generated, I get the leader node to publish a block to the ledger just for safekeeping. So if we go now, so this was sequence number 50. So if I go and hit my API, and we scroll down here to the bottom, we can see that I just get him, the leader node, to publish a transaction of all of the proofs. So these are all the proofs from all the 12 nodes or 10 nodes, and they're all the same, which means that it's verified on chain that everyone has generated the same key. So that's just a little extra bit of sort of transparency that I decided to implement with the pBFT. So now that that is done, we also have we have derived the Bitcoin address. So this is the Bitcoin address that we can send deposits to enact a bridge. Now, I've only started working on the API for the Bitcoin deposit watcher, but how I would imagine could work, or how I'm going to implement it, is if I have a terminal here, is when one of these keys gets generated, what I would do is I would have a worker running in the background, which is not implemented yet. It is going to be implemented by this test script, or it's going to be simulated by this test script. And this pretty much watches out for deposits to Bitcoin addresses. So I made a deposit to this Bitcoin address earlier, just before this video, and that's what's being picked up here. So that's that TXID, the amount, which is what, 57,000 satoshis, and the block and all that. So the way that this bridge would end up working is this information here will be hashed into some byte string, and the hash of this payload will um, end up being the message that gets signed by all of these nodes in this signing process. So we can initiate now a signing process um, to sign a bit of data like that. And the result of the signing process will give us a signature. And what we can do with the signature is we can recover from it the public key or the original owner who signed that message. So the signature pretty much gives us proof that someone has done an action on our behalf. So we can see here that the address that we get is the same address that we derived above. So how I'm going to implement this now is the signature that we calculate or the transaction that we sent. I'm going to hash that and then store that as a transaction in the push that to the ledger, and then recalculate the signature in a smart contract and reverse engineer the owner's address. And if the owner's address is equal to the shared or the node's public key that we have derived here, this address, or the Ethereum version of it rather, then we can safely do a mint. So that's how I have come to find that native Bitcoin bridges and things work. So yeah, so this is pretty much it for episode 2 of this documentation, if you will. So signing and key generation have been done, and now I'm just sort of interfacing with the Bitcoin API to watch out for deposits and to sort of make this whole signing process autonomous as I deposit, instead of me having to execute commands as I've been having to do here. So yeah, hopefully in part 3 I'll have like the whole back end working, and then in part 4 I'll make like a front end so you can actually go and deposit to an address, wait a few minutes, and then receive your minted Bitcoin on Ethereum. So yeah,